All right, welcome back to our discussion of metabolism, Chapter 8 of Campbell's Biology. We're going to move here to Concept 8.2. So the free energy change of a reaction tells us whether or not the reaction occurs spontaneously. So there are reactions which occur by themselves all the time, and there are reactions that don't and need help. So, as biologists are interested in which ones are spontaneous and which ones require energy, because this helps us to understand how processes fit together. Because oftentimes things that require energy are getting that energy from spontaneous reactions. So we need to be able to determine energy changes, okay? We use this with a calculation, and um, what we do is we measure what we call free energy. Okay, this is the energy that is either gained or lost, and that energy can then be um, used to do something or transformed into some other form of energy. Now, when we measure this, we do it in a controlled setting so that we have a uniform temperature and pressure. Um, but that's not very important to us right now. I'm about to show you an equation, and I don't want you to get overly hung up on it. You do not need to be able to use this calculation at this point or to fully understand it. I just want to introduce you to it, okay? So let's start utilizing some different terms. So when we refer to a change in free energy, we're going to refer to that as delta G. Okay. This is a G named after a person by the last name of Gibbs. Oftentimes this is called Gibbs free energy. All right, and this change in free energy has to come from somewhere, right? So there are two ways that we can get it. One is by changing enthalpy, or the actual potential energy within a molecule, or we could gain it by a change in entropy. We could also get it by absorbing temperature energy. Okay, so we can put all of these together into an equation where the free energy of a system is equal to the change in energy of a molecule, or the enthalpy, the inherent energy, chemical energy stored in a molecule, minus the temperature times the change in entropy. Now, the important part of this is only processes that have a negative delta G are going to occur spontaneously. How do we get a negative delta G? Well, if we had a very high temperature, that would produce a negative delta G because we have minus temperature, right? So as the temperature increases, the likelihood of delta G being negative goes up. That's why things tend to occur better if you heat it up. This is also true for a change in entropy. Remember the second law of thermodynamics. Once an increase in entropy, here, it has a negative sign in front of it. So a increase in entropy produces a negative delta G. Okay, so these are two ways that we can get there. The third way is if you take something that has a lot of potential energy and then reduce that amount of potential energy. So we go from maybe 100 down to 50, right? That would produce a negative 50 in change in energy. So all these ways we can produce a negative delta G and cause a reaction to move forward. Okay. Now, these spontaneous processes can be harnessed to perform other work, such as building work. So, reactions that require input of energy, we might be able to harvest it by coupling it to something that would happen anyway. Okay. So let's think about this change in delta G and this potential energy storage and this entropy change. And we'll do it in in a couple different forms here. So here's a diver on a diving board. It has a lot of potential energy because the diving board is holding him off the surface. You take that away or you step off of it, all of a sudden all that becomes um, potential energy or becomes kinetic energy. So that is essentially a negative delta G, right? Or in this case, it's a negative, both of entropy and enthalpy are changed, but it produces a liberation of energy. So here we have more energy, less stable, because up here you could fall off. So you can imagine it being less stable. And this has a capacity to do more work if it's liberated. Okay. Once you've fallen off and you hit the water, that's about as uh, random and highest entropy you can get. So in that circumstance, you are more stable because you're already down. You can't fall any lower, right? So in this case, you have less capacity to do work. Well, this is true at every single level, right? So here's a bunch of molecules, and if you release them into an environment, they're going to diffuse or disperse, right? This is a change or a negative change in delta G. So here we have more order, less stable, more capacity to do work. Here we have very low capacity to do work, but it's very stable. Here we have a sugar molecule. So this is glucose. We can take glucose and break it down into smaller things. So here's some water molecules, and here's some carbon dioxide. You can see that this is more disordered. This is more structured, so it has more stored energy, but consequently it's less stable. Here, more stable, but less stored energy. And this process of going from one to the other releases energy, and that energy can be coupled to other things. So, when you have a reaction that is spontaneous and has a negative G, we call that an exergonic reaction, right? So you light a piece of paper on fire, the paper is going to continue to burn, right? It's just going to burn and burn until it's all gone. This is kind of a spontaneous type of process. Energonic is when a reaction would require an absorption of energy in order to make it happen. So it's not going to happen on its own. It requires that energy input. Looking at it in a graphical form, here we have the amount of free energy on this axis. Here we have time moving forward. So here we have reactants, which have a lot of stored energy. You are going to turn it into its products, and it's going to release that energy. That energy released is a negative delta G. Okay. Here is the opposite scenario where you have reactants that have low potential energy. And if you capture energy from, say, over here and add it in here, you can combine it together with other molecules, forming larger, more complex things. That more complex thing is going to essentially store all that energy that we put into it, and it's going to be less stable. But that is a positive delta G because we are gaining energy in the molecule. Now, as reactions carry forward, they can reach a point where you reach an equilibrium point. An easy way of demonstrating this is looking at a water tower and some type of uh, hydrothermal generator of some kind. So here we have water in a tank. Here we have another tank that is lower. That water can run through, and as that water runs through, we can harvest some of that energy to turn this wheel, and that wheel turning will turn a generator, which generates electricity. Okay. If this is a closed system, sooner or later, that water is all going to reach the same level. Okay. In this circumstance, this is what we call equilibrium. And it is the delta G in this scenario is 0. So essentially nothing is happening. Here, because we have all this water up here and gravity is dragging it down, we have a negative delta G. The water is going to spontaneously flow down this ramp. Okay. So cells are not in equilibrium. They are open systems and have a constant flow of material. We are constantly eating, constantly utilizing that material, breaking it down, storing the energy, using it. We're constantly dissipating that heat into the environment. Okay. So we are not a closed system. We are open and we are not in equilibrium. That's kind of a defining feature of life, is that we are not at equilibrium. If we actually achieve equilibrium, we are dead. Now, catabolic pathways release energy, okay, by breaking complex things down into simpler ones, but we do it in a series of reactions. We don't do it in one fell swoop. Now, something that will come back later is just because the cell itself is not in equilibrium doesn't mean that a particular reaction isn't in equilibrium. So there are reactions that occur in the cell that tend to be at equilibrium. But in net, all of the reactions together are not in equilibrium. So coming back to this idea of doing several small steps and putting it into our water wheel analogy, we could take all of this water and just rush it down here and gain a little bit of energy. And now to keep this an open system, we have to constantly be putting more water in, and that water has to have somewhere to go out here to prevent equilibrium from forming. Here, what we've done is put several of these in a row, and here we can keep utilizing energy as the water flows down, right? This is what our body does. Instead of doing a reaction in one fell swoop, we do it in small little steps. So, for example, if you were to take a sugar cube and light it on fire, you could burn it, and it would instantly turn into carbon dioxide. That generates a lot of light and a lot of heat, okay? But that would be also very destructive for our cells. So we have to do it in small little steps and gain just a little bit of energy along the way. So concept 8.2, free energy change of a reaction tells us whether or not reaction will occur spontaneously. We introduce the idea of a free energy being delta G, and that's related to the total amount of energy or enthalpy in a molecule. So more complex is more energy. And we relate this to temperature and enthalpy, and we know that only processes that have a negative delta G are going to be spontaneous. Graphically, we can show this in terms of a reaction that has a negative delta G. So we have something more complex becoming more simple that has a lot of potential energy. It is now released as free energy, so that is a negative delta G. We would refer to this as an exergonic reaction because has a negative delta G. It is releasing energy. Endergonic reactions require an input of energy. What we do is when we